Now I want to explain an article from Microsoft Semantic Machines and also Allen Institute for AI. This article is written in 2022, Successive Prompting for Decomposing Complex Question. And also there are very related ideas that are very interesting, such as partial, that they use it for some programs, or this one, machine reading comprehension using case-based reasoning, or this one from Tsinghua University. But let's focus on this article from Microsoft. Of course, there are other articles. For example, I've explained this article in my playlist for deep learning. And this article is also interesting. So what is question decomposition? We propose successive prompting where we iteratively decompose the complex question into the next simple question to answer it, and then repeat until the question is answered. The complex question is answered. So when we say who kicked the longest field goal in the first half, first we should ask what are all the field goals in the first half. One of them is in 12 yard, the other one is in 42 yard. And then we ask what is the largest value in those things? So the answer is 42. And then we ask who kicked the 42. So we use this to generate another question. Who kicked the 42 yard? Then we get an answer. So this is the final answer because there is no question anymore. We introduce successive prompting where we iteratively break down a complex task into a simpler task, solve it, and then repeat the process until we get the final solution. Successive prompting decouples the supervision for decomposing complex questions from the supervision for answering simpler questions, allowing us to have multiple opportunities to query in context examples at each reasoning step. Learn question decomposition separately from question answering, including using synthetic data, and use bespoke fine-tuned components for reasoning steps where a large language model does not perform well. Since the decomposition and answering steps are performed separately, we can decouple the supervision of each step, providing two primary benefits. First, when performing in context learning, we get multiple opportunities to select different in-context examples, which can be tailored to the particular decomposition or answering step being performed, instead of selecting a single set of examples based only on the complex question. Second, when fine-tuning with or without in-context examples, we can provide training examples for each step independently, so the model only has to learn to perform one step at a time. So the goal of compositional question answering is to answer a complex question in context of passage by reasoning through latent sequential decisions, Z1, Z2, Zs, to reach a final answer. Many models have been proposed to accomplish this with varying amount of supervision and interpretability. For example, I explained chain of thought. The latent steps are supervised, interpretable sentences. In other models, these latent steps might be a program, or even just like the unsupervised hidden states in this article. We focus on models that take in context examples and produce a discrete language encoded Z. So in successive prompting, we present each latent step as a pair of simple question and answer. So what is in-context learning? During in-context learning, a small number of training examples are provided directly in the prompt that is given to a large language model before the test input. These examples are selected from an index based on their similarity with the test input. For successive prompting, we create two indices for looking up relevant demonstrations, for question answering. And that index contains partially decomposed chains at each step, demonstrating the next question to be produced for every complex question in training data. And for fine-tuning, we use T5-based sequence-to-sequence models. Such models are typically trained with control codes in a multitask setting. And this is a synthetic dataset. Inspired by Euron, we use semi-structured data from tables in English Wikipedia, which is available in plenty. We employ curated templates to convert the rows in the tables into paragraphs. We use single column headers to create first order simple questions and a combination of columns for higher order complex questions. We synthesize data for 10 simple operations: filter, comparison. So it reminds me of my own article that I wrote using the dataset of Breck dataset that is developed in Israel. It's a very nice dataset. So it has a semantic, I used the word semantic operator because we wanted to predict these operators, these kind of, and also they use the word operator here as well, operations. So we generate the higher order combinations of first order operations wherever possible. Figure 3 shows examples of higher order combinations of the atomic operation count with a few other simple operations. So how many opponents were there? The question is, what are all opponents? And then we say we count them. The count, for example, what are in the answers? We use this. And then we say how many items are in the list. Another reason is higher order decomposition. Because sometimes you need more than just one operator count. We need, for example, two operators, such as sort and then count. Or here, first you do comparison operator, and then you use count operator. It's just very similar to that idea of Allen Institute. Of course, because this article is also written by Allen Institute, so I see the inspirations. So there are different operators: filter, count, comparison. So we have a complex question, we decompose it into simpler questions. First, for example, we filter it and count it, or we understand here we count it. We then use a comparison like if then, or sometimes a combination of operators such as sort and then filter. And then difference and then sort. Or other examples like count and then filter. How many rounds is count? And this is the filter. So we are decomposing it using these operators. Higher order combinations.